We are going to talk about two important types of algorithms, or two classes of algorithms that perform search and sorting on a sequence of values. And of course, algorithms are not confined to these two functions, but they are two of the most elementary functions of algorithms, and they come up so frequently that many algorithms have been devised to perform these functions. So we are going to a little bit briefly study these search and sort algorithms. Of course, there are a number of algorithms for other functions which we will not study, but the main idea here is to acquaint you with the concept of an algorithm, how to design it, what to be careful about, and of course to give you a familiarity with important algorithms such as searching and sorting. And the first one we are going to talk about is called the linear search. And this is for searching a value in a given sequence. So what you are after is, if the value exists in the sequence, you would like to obtain the position where it appears in this sequence, or if it doesn't, here I'm going to use a zero to indicate that case. So my input is a sequence A1 through AN, as well as a search key X. Now, these could be numerical values, but depending on your structure, your program, this may be some other structure, maybe a text, maybe a class, if you know what that is, or an object of a class, let's say, or some data structure, or any value and any construct you can think of can be the input of this algorithm, as long as you can define an equality checking operation. So what you do is quite straightforward. Well, think about how you would search for a value in a list. You would just look for the value one by one. So look at the first position, A1. Is the value I'm looking for at position number one? If so, then return the position, which is 1 in this case, or in general I. If not, just look at the next value, then look at the next value, then look at the next value until you find it or you reach the end of the sequence. So what you do is you have a loop here from 1 to n, the end of the sequence. You just one by one check whether the value appears in this sequence. If you find it, if one of the values in your sequence a sub I equals x, your search key, then you return I, which indicates the position of the value you are searching. If you do not, that means you exhaust all the values in your sequence and you could not find your search key, then you return 0 to indicate that this search key does not exist in the sequence. So this is essentially linear search. An alternative to this is what we call the binary search. Now, there is an essential difference between linear search and binary search in that um, in linear search, the sequence does not have any particular specific properties, whereas in binary search, you require the input to be sorted. Okay, so here we are going to assume it's in ascending order, and that will help us because if you know that your sequence is sorted, what you do is, suppose that your sequence is 1, 3, 7, 9, 12, 15, and 25, and you are looking for 7, your search key. If you know your data is already sorted, then what you do is you don't need to go looking for it one by one. What you do is you look at the middle of your list. So I have 1, 2, 3, 4, 5, 6, 7 elements here. So I'm going to look at the middle position, which is 9 here, because I have 3 elements here and 3 elements to the right. Then this is the midpoint. Now I compare this to my search key, and my search key, which is 7, is smaller. Therefore, I'm guaranteed that my search key will not appear in the right hand side, because they are already greater than the middle of the list, and the middle of the list is greater than my search key. So my search key, if it exists in this sequence, has to be on the left half. So I don't even need to look at the right half of this sequence. And here, well, if you like, you could include this also. You will have to look at, again, the midpoint. Now, in this case, of course, implementations may differ, but if you actually look at the pseudocode provided here, what you do is you have 2 indicators, left and right, to show the endpoints of your list, and the middle indicator, which points to the midpoint. And here it's defined as L plus R divided by 2. Of course, this would be integer division. So here in this case, if L is L starts with 1 and R starts with 7, because we have 7 elements, 7 plus 1, 8 divided by 2 is 4. So it points to 9. But when I update my pointers, since my search key is smaller than this midpoint, I'm going to ignore the right half, and I'm going to focus on just this one. So left becomes, well, it stays 1, but then right becomes this old midpoint. So M here becomes 4, R, so R becomes 4, and left here stays 1. So 4 plus 1, 5, divided by 2, 2.5. So that's not really 2.5. Integer division should give you 2. So this here is your mid value, okay? And my search key is 7. Therefore, I'm guaranteed to not find it in this left side. So I'll have to look at this right-hand side. In this case, I'm going to update my left indicator to 2. My right indicator is still 4. In the next iteration, again, look at the midpoint, which is 2 plus 4 divided by 2. You get 3. So 3 is here. And it exactly carries my search key, in which case I return the position of this point. But this iteration, you see, will push the left indicator and the right indicator towards each other, and at some point they are going to converge on each other. At that point, they are going to point to the same value, and if that value that both of them point to is equal to your search key, then return that position. If not, your search key does not exist in the sequence, and then in this case you return 0. So this is how binary search works. And essentially, since you cut the size of the problem in half at each iteration, you see, or you perform less number of comparisons with respect to linear search. So we will see that binary search is actually better than linear search in terms of time complexity.